to the Circuits Lab tutorial series in the University of Miami's College of Engineering. So today I'd like to show you the second in our series, Breadboards 2. We'll be getting a closer look at the breadboard and learning some general tips and tricks for your circuit.
As you may already know, a breadboard is a device that effectively replaces the need to permanently solder electrical components to a PCB board. Instead, the many slots of a breadboard allow us to temporarily fasten our components together for projects and prototyping, and then take them back out when we're done, making both board and components reusable. What makes a breadboard so useful is the fact that each of those holes are connected in rows. You can think of row 1 and A, B, C, D, and E as all being connected by a metal strip underneath, acting as a node. In the center, we have many horizontal rows, which we commonly use in the main portions of our circuits. But on either side, these vertical rows serve a special purpose. There is one entire long strip running underneath this row, and another one, this one. These large nodes can serve as an easy access to ground or VCC for your circuit, as we'll see right now.
Now, I've connected all those strips with jumper wires, and this is where those side strips come in handy. As you can see, all the yellows are interconnected and form actually in effect one long strip, and I've done the same with green. Now, in this way, you can create a ground state all on the outer edges and a VCC input on the inner edges, typically at 5 volts.
Translating what we see in an electrical schematic to a real-world circuit can be challenging sometimes, especially if you're new to building your own circuits. Here I have a simple example of 3 resistors in parallel, grounded, and powered by a VCC voltage. In any given schematic, we see the elements arranged in one specific way, but a real-world circuit can be arranged in many different ways, as long as everything is still electrically equivalent. This is the part where your creativity comes in. So what exactly do I mean?
Here's an example of 3 resistors in parallel, each sharing a top node and a bottom node. And as you can see, these hook by a wire directly to VCC and down here directly to ground. How about this circuit? Is there any difference? Actually, there isn't. Electrically, this is exactly the same as the thing I showed you last time. Right here, we have this connected to VCC. The top of this resistor is connected to VCC, and so is this one. This connects right here, and now this whole strip counts as the node as well. This is all still the top node. And as you can see, they all come down here and become the ground node, which goes straight back to ground. Here's another equivalent circuit. Here, it's a little easy to tell that these all share the VCC node, but watch where these go. This resistor goes here, this resistor grounds right here, and this one goes over here. They all still share the same ground node. It's exactly the same as before.
I'd like to give a brief mention to electrolytic capacitors. Unlike ceramic capacitors, the electrolytic kind do have a specific positive and negative end. The positive lead is usually longer than the negative. Another way to get your leads right is to check the capacitor body itself. There will be a telltale marking on the side to indicate the negative lead. Make sure your electrolytic capacitors are always connected correctly, otherwise you could have a very bad day. For light-emitting diodes, or LEDs, it's oftentimes difficult to tell which lead is the positive one and which is the negative. There is a little notch at the positive end of most LEDs, but the easiest way to visually tell which end is which is to look at the length, just like the capacitor. The positive is longer.
Now, breadboards are designed so that you can place an IC directly across this little gap over here and bridge it by carefully pushing in all of the pins very gently, and you make sure they're well aligned. Now, each of these pins has an entire node to itself, which you can do a lot of things with.
Here's a demonstration of a more complex and fully functional circuit. This is an analog to digital converter, which you may encounter soon. Notice how the LEDs display a binary code relating to the changing analog voltage.
Thanks for joining us for Breadboards Part 2 of this tutorial series. We hope that this has served to clear up some of those confusions and questions you may have had about building circuits. Now go out there and build stuff.